Let's look at two important properties of LCM and HCF. The first property reads as follows. Product of two numbers is equal to the product of LCM and HCF of those two numbers. Let's say the two numbers are A and B, and let their LCM and HCF be L and H. So what this property essentially states is product of the two numbers A into B is equal to product of the LCM and HCF of these two numbers, which is L into H. Let's take a simple example and check whether it works. Let's take A to be equal to 10 and B to be equal to 12. So product of A and B, A into B is equal to 120. Let's set about finding out the HCF and LCM of these two numbers. So first step, let's prime factorize 10. 10 will prime factorize as 2 into 5. 12 will prime factorize as 4 into 3, which is a 2 square into 3. Let's find out the HCF and the LCM. HCF is the product of lowest powers of common primes. The only prime common to both these numbers is a 2. The lowest power of 2 is 2 power 1. So the HCF is equal to 2. LCM is a product of the highest power of all primes. Let's list down all the primes 2, 3 and 5. Highest power of 2 is equal to square of 2 because 2 is present in both the numbers. Between the two numbers, 2 square is a larger power. Into 3 into 5. 3 and 5 are present in only one of these two numbers. So they appear in the power in which they appear, which is 1. So LCM is equal to 2 square into 3 into 5, which is 4 into 3, 12, 12 into 5, which is equal to 60. The product of the HCF and LCM, which is 2 into 60, is also equal to 120. So product of two numbers is equal to product of the LCM and HCF of these two numbers. Quickly see it in a printed form. This is what the property essentially means. Taking the example, we prime factorize 10 and 12 to get us 2 into 5 and 2 square into 3. HCF is product of lowest power of common primes, which is 2. LCM is equal to product of all primes in their highest power, which is equal to 60. Product of A and B is equal to 120. Product of the LCM and A and B, LCM of A and B is equal to 120. So this is proved. Now let's look at why this works. Let's just take a couple of minutes to understand why this is working. Let's go with this example itself. Let's go with this 10 and 12. 10 prime factorized as 2 into 5. 12 prime factorized as 2 square into 3. The product of these two numbers is a product of these four components. 2 into 5 into 2 square into 3. Now, when we found out the HCF, what is the definition of HCF? HCF is product of lowest power of common primes. We have only two numbers with us. So if a prime is appearing in more than one number, the lower power comes to the HCF. Here we have only one prime appearing in both the numbers, so pick 2 as the HCF. So I'm going to circle 2, the number from these four parts which has come into your HCF. Now let's look at what our LCM is. LCM is a product of all primes. So you need to write 2, 3 and 5 in their highest power. If a prime appeared in more than one number, the highest power comes to the LCM. So 2 square comes here. If a prime appeared in only one of these numbers, it's going to come in whatever power it is available. So LCM had 2 square into 3 into 5. Let's put these components with a square. So squares are LCM, circles are your HCF. So square has a 5, this and this. So if a prime appeared in only one of the numbers, as was the case with 5 and 3, it came into your LCM. If a prime appeared more than once, it's going to appear twice because you're talking about two numbers. So it can appear with a higher power and a lower power. The lower power came to your HCF and the higher power went to your LCM. So essentially, there are four parts to this product. We have split them in a different order and got them in the LCF and LCM. So product of this should be equal to the product of this, which is why this method works. The obvious question is, can we extend this to beyond two numbers? Let's take one example to see whether it works. Let's look at the same 10, 12. Let's add one more number. Let's say we add a 6. 10 is a 2 into 5. 12 is a 2 square into 3. This number is a 2 into 3. HCF quickly. Only prime common to all the numbers is a 2. In its lowest power is 2. LCM, write down all the primes, which is 2, 3 and 5. In the respective highest powers, which is 2 square into 3 into 5. I'm just going to mark wherever I'm going to pick at HCF. HCF, let's say, is a 2. We picked it up from this. LCM, I'm just going to block it with rectangles. So let's mark it with rectangles here or squares. 5 is a part of your LCM, 3 is a part of your LCM, and 2 square is a part of your LCM. The product of these three numbers would have had 6 parts to it. The LCM and HCF together have accounted for only 4 out of the 6 parts. So the product of the three numbers need not be equal to the product of the LCM and HCF of these three numbers. So for two numbers, it will certainly work. Beyond two numbers, it may not work. The numbers are prime, it will work. So keep this factor in mind. Do not extend it to beyond two numbers in general. Second property that I want to walk you through is the LCM is always a multiple of the HCF, or the HCF is always a factor of the LCM. Why is it so? Start with this. Let's take the numbers to be A and B and the LCM and HCF to be L and H. H is the factor of A and B because if H is a HCF of A and B, it's a common factor to both these numbers, which means it should be a factor of both the numbers. So I can say A is divisible by H and B is also divisible by H. Right? That is established. Now, L is a LCM of both these numbers A and B, which means L is a multiple of A, L is a multiple of B, which means L is divisible by A and L is divisible by B. Here we have a number L, which is divisible by A and B, which in turn are divisible by H, which means that L will be divisible by H. So H is going to be a factor of L, or L will be a multiple of H. So anytime, for example, if someone says the LCM of two numbers is 16 and their HCF is equal to 6, is it possible? Obviously not. 6 is not a factor of 16. Therefore, you can't have the LCM of two numbers to be 16 and their HCF to be equal to 6. So it's a quick validation. After finding the LCM and HCF of two numbers, check out whether the LCM is a multiple of the HCF. Conversely, is the HCF a factor of the LCM? If it is not, as it turned out to be in this case, then you made some mistake. So it's a way to validate whether your LCM and HCF are correct.